All right, so this video is on figuring out the pH of a solution that contains a weak acid. Now, let's just quickly review when we have a strong acid. For a strong acid like HCl, which I've done at the bottom here because that's not the focus, for every 1 mole of this, you're going to get 1 mole of this. Essentially, you can think of it as completely dissolving, but it really isn't dissolving, it completely ionizes. Okay? And what that means is if it's 1 molar HCl, you really have 1 molar H plus. That's equal to the concentration of hydronium. So you basically just take the the negative log of that of 1, and you get 0. Okay. If let's say you had a 10 molar solution of hydrochloric acid, right? Then you'd have like the negative log of 10. And the log of 10 is equal to 1. So when you negate that, you'd actually get a negative pH, and that's possible. That's a highly concentrated solution. But it does have, in fact, a negative pH, and that's possible. So you can have pHs below 0, and you can have ones above 14. They would just have to be very concentrated acid or very concentrated base solutions, respectively. Now, for a weak acid, the math is a little different, because for this one, for 1 molar HC2H3O2, or acetic acid or vinegar, the Ka value here is equal to 1.8 times 10 to the minus 5. What's important to recognize is this means that very little of this actually ionizes. Now, the amount of ionization will vary, and we're going to find that when we dilute it, it will ionize to a greater degree. But while this is 1 molar, a 1 molar solution of HCl has a pH of 0, the 1 molar of the vinegar is not going to have a pH that's as low as that, because when you look at what's happening and you kind of understand what's going on here, in this beaker, I've just got H pluses and Cl minuses, and that's it. Right? If I have a beaker of 1 molar vinegar, I have a lot of I've got a lot of the acid that's unionized, right? And I've got a small amount of H pluses and A minuses. Most of it stays together as the full acid. I didn't want to write out the acetate ion, so I just wrote HA. Okay? So we have to write out the expression. So for this one, we have the Ka, is equal to the acetate ion, right, times the H3O plus, okay, over the unionized acids, the HC2H3O2. And we can do this by ice table. We're going to assume that this is starting at 1, right? And so it's going to go down by x. And these guys are starting at 0 over here. And so they're each going to go up by x. So we can now plug this into our equation. So we now have 1.8 times 10 to the minus 5 equals, it's going to be x on top. I didn't write my equilibrium line here, but these are going to be obvious. 0 plus x is x. 0 plus x is x. On the bottom here, I'm going to have 1 minus x. The assumption we can usually make here is that this value of x is really small. And we want to make sure we can assume this is approximately equal to, okay, x squared over 1. Why can we assume that? Because this x is going to be small. And because Ka is a small value, we get very low product, which means this guy, the really weak acid, okay, remember, it's survival of the weakest. That guy survives. He's barely changed. Okay? So we're going to assume x is less than 5%. And we're going to call that percentage now, okay, percent dissociation or percent ionization. Okay? And that percent ionization should be less than 5% if our assumption is valid. So we take the square root of this thing. And when we solve for x, what we get is we get 0.00042. And that's equal to our H plus concentration. It's also equal to the acetate concentration. And we can then take the negative log of that value, which I'm going to do right now, and press my log function and go 0.0042, put in parentheses, and what I get is 2.37 is my pH. This is not as acidic as the 1 molar solution of hydrochloric acid. Both of these solutions are of equal concentration, okay? But because of the lesser degree of ionization of the weak acid, we have less of the H pluses, and that's what this is really all about, and therefore we have a higher pH. We could also, of course, figure out the pOH by subtraction from 14. We could figure out the OH minus concentration for this as well. I'm not going to do that. What I really want to focus here on is the percent ionization. So if I take the 0.0042 and I put that over the 1 and I times it by 100, what I get is a percent ionization of basically 0.42%. And that 0.42% means that, well, it means like a very small percentage change. It means if I ask the final concentration of the acid, it's 1 minus 0.42, which means it's like 0.96. Okay, so less than 5%. Okay, of that has changed. That's the percent ionization. Now, watch what happens when I dilute the vinegar, right? So let's say I do 0.01 molar, and we do the exact math all over again, right? So we're still exactly the same thing. We have 1.8 times 10 to the minus 5, right? We got X up here, that's the hydronium. X, that's the other anion. And down here again, we have 0.01 minus X. So the math is always kind of the same thing, which means we end up with X squared on the top. And again, we're making this assumption. We're going to put the 0.01 on the bottom. Now, when we cross multiply, okay, this is really like 10. This is the same as saying is equal to X squared over 10 to the minus 2, right? And so when you bring this over to here and multiply this, you end up that X squared is equal to 1.8 times 10 to the minus 7. And when we take the square root of that, we get a different value. When we take the square root of that, we get, I believe, and I might be slightly off by this, I got 0.000134. Okay? Now, what's important here is I can get the pH of this, which I'm going to do. Hold on. So the pH I get now is 3.87. Now, the interesting thing, this is less acidic, right? Because it's got a higher pH. But the percent ionization is greater. And what you can think of this is, I'm going to go back to the page. You can think that as you're adding water, it's causing it to shift to the right, which means you're actually causing the concentrations, the more ions to form. But you're also lowering the concentration at the same time. So the percent ionization goes up while the concentration goes down because you're diluting it. So in the end, even though it's less acidic, the percent that actually ionizes is greater. And you can just do the math here. So you take the 0.000134 and you put this over the 0.01, which I'm going to do right now. And when you do that, you get, let's see, 0.000134 divided by 0.01, and you get, times 100, sorry. And I'm going to put that in times 100 because we always want 1%. You get 1.34% ionization. Whereas in the previous question, it was something like 3% ionization. So as you dilute things, okay, you get a greater degree of ionization always.